By the way, I was not able to solve D today. Like, I have the solution with me, but I won't be discussing it because the system testing is right now still going, and I'm not going to discuss something until it's accepted. So I'm going to discuss A, B, C, and then F. So these are the 4 problems that I'm going to discuss. Okay. So like problem D was also easy, but like I couldn't submit it on time earlier. Like I wasted my time. I read the problem statement incorrectly. First, like I was confused for that problem. Anyway, so let me start my screen share. So my screen is visible, right? Let me zoom in a little. Okay, perfect. So in this problem, we are given that we have an array of n integers, and we can do some operations. In one operation, we can choose a non-negative integer m, and such that 2 to the power m is less than or equals to n. So basically, we can select any m such that 2 to the power m, like the number of elements in the prefix that we are choosing, is less than or equals to n. Then we can subtract 1 from all the integers in the prefix, like in the first 2 to the power m elements. So we have to find whether it's possible for us to make the array a non-decreasing one. So the only thing that we have to notice in this problem, see, if you're doing some operation, let's say if you're doing some operation, let's suppose we are doing operation on these 4 elements. So the value, the relative value of all of these 4 elements won't change, right? If it was x earlier and this was y earlier, this will now be x minus 1 and y minus 1. So the relative difference between these two values won't change. The only, like after any operation, only the relative like the absolute difference between the values that will change is these two. That is the element which is here and the element which is here. And in a non-increasing array, in a non-decreasing array, we need to maintain that ai is less than equals to a of I plus 1, right? So if you look at two adjacent values after an operation, only these two, like the difference between these two will change. So we know that we can change the difference between 1, 2, the difference between 2 and 3. Why? Like these are powers of 2, or 4 and 5, 8 and 9, and 16 and 17. So these are the only like only places at which we can change the relative difference or the absolute difference between two values. So in input n is less than or equals to 20. So we just had to do this, that in case I is more than a of I plus 1, I should be one of these. If it is not, then then we won't be able to make it a non-decreasing array. Is it clear? Yes, no, anything? Okay, let me show you the implementation. So this is the implementation. In this, I'm just checking that if a of I minus 1, because I'm starting from 1, if a of I minus 1 is more than a of I, then I should be one of these. If it is not, then f is 0, and we can simply continue. So going to the next problem, we are given that we have an array a of length n consisting of positive integers and an array x of length q. Now, this second array is of also positive integers, and there will be q modifications on the first array. In the ith modification, we choose some, like for every I between 1 to q, we'll do like the ith modification will take place. In this, we will choose every j between 1 to n, like all the elements in AI which are divisible by 2 to the power xi, and we are going to add 2 to the power xi minus 1 to aj. So I'll explain this in a moment. Now xi for every value, like every value in array x is between 1 and 30. So what we have to do, see, this is our array A, this is our array X. So if let's say if there's a 2 here, we will find all the values in this array that are divisible by 2 to the power 2, that is 4. And then all of those values, we will add 2 to the power 2 minus 1, that is 2 to the power 1, which is 2. So first of all, just if we look at these operations, if a number is divisible by 2 to the power x, if a number was divisible by 2 to the power x earlier, after doing one operation, it won't be divisible by 2 to the power x. Why? Because we are adding 2 to the power x minus 1. Like if the number earlier was divisible by 2 to the power x completely, it won't be divisible by it now. Why? Because we've added this thing, right? There will always be a remainder left because this thing is not divisible by 2 to the power x. But now it will be divisible by 2 to the power x minus 1. Why? Because earlier the complete number was divisible by 2 to the power x. Now we have added this. This is also divisible by 2 to the power x minus 1, and this is also divisible by 2 to the power x minus 1. So these operations are very simple. We'll perform operations like we only have, let's make a list of 30, like of size 30. This is a list of size 30. In this, 1 is like all the numbers which are divisible by 2 to the power 1. 2 holds all the indices that are divisible by 2 to the power 2, like this, 2 to the power 30. So we'll perform one operation. Let's say currently we're getting xi. Let's say xi is this. We know all of these numbers, like not only xi but xi plus 1 also, right? Xi plus 1. These are also divisible by 2 to the power xi. So we will shift all of these lists to this xi minus 1. Like this complete, let's say there was 1, 3, 7, 2, 9, and 11. So these are the elements that, like, these were divisible by xi, these were divisible by xi plus 1, this index, and 9 and 11. So what we'll do, first of all, we'll add to, like, these indices, we will add 2 to the power xi, and we will shift all of these indices to this list. Like this list will now get bigger. So if you look at time complexity, it is nothing but, see, what is the worst case? Each index can go from this to this. So how many times it can get shifted? 30 times only. So 30 times n is the time complexity. And this is also the space complexity. Is it clear? What about others? Is it clear? If anyone is having any doubt, you can unmute and ask me. Okay, I'll take a test case. So let's take 1, 2, 3, 4, 4. So we have 2, 3, 4. So from 1, like this is my list. So 1, 2, 3. So from 2 to the power 2, these two indices are divisible, like the numbers which are presented, these two indices. So it is nothing but 4 and 5. And 2 to the power 1 divides 2 to the power 1 divides the numbers at this thing. So this is nothing but index 1, right? And 2 to the power 0 divides this thing and this thing. So 1 and 3. And this is index 2, because all the indices are 1 index. Now you just have to check if you are at 2, at these indices at 2 to the power, so this becomes plus 4, and then remove these numbers from here and shift to them to the previous 4.5. Then you do 3, the list is empty. For 4, it's also empty. So the answer becomes 1, 2, 3. What did I add? I think I have done something wrong. Just give me. I have added 2 to the power 2. 2 to the power 2 to the power 2 minus 1. Right? I added 2 to the power 2, 2 to the power 2 minus 1. That will so you'll add 2 and 2 here. So after the operations, this will become 1, 2, 3, and 6 and 6. Is it clear? So now if you do these operations in one each here, there's no point in forming these operations. Right? And actually xi is like, you will never get xi as 0. You will always get xi as 1. So you can perform these operations again and again. The numbers cannot go beyond this. Like they cannot go any position to the left of this. So that's why how many times a number will shift, index will shift only 30 times. The complexity is times n. Is it clear now? Yes, no, anything? Okay, so let me show you the implementation. So first I'm taking n and q as input. Then I'm taking array A and X as input. Then for all the devices, like I'm finding from 30 to 0. First of all, if the ith number is already included in a list, don't include it in another list. So I'll simply continue if ith number or ith index, the number which is presented ith index has been included in some list. Otherwise, if a of I is divisible by 2 to the power b, then I'll include it in the bth list. So there are 30 lists, right? There are 31 lists, 0 to 30. Then for every value in x, what I'll do, I'll go from like every list from E to 30 and just remove all those numbers from that list and include them in the E minus 1th list. Then add this thing to your AI. Finally, clear your bth list. Then you can print your array. So is it clear? Okay. So going to the next problem. In this, we are given that a boy Smilo is playing a new game, and in this game there are n hoarders of monsters, and the ith hoard contains AI monsters. So the goal of this game is to destroy all the monsters, and to do this, we can have two types of attacks and a combo counter X, which is initially set to 0. So the first type of attack, we choose a number I from 1 to n, and this should be such that there is at least one monster left in the horde with the number I. Then we can kill one monster from the horde number I, and the combo counter X increases by 1. The second type is that we choose a number I from 1 to n, and such that there are at least X monsters left in the horde with the number I. Then we can use an ultimate attack and kill X monsters from the horde with the number I. After that, X is set to 0. So we have to find the minimum number of operations required like this. So let's say there are, this is the first horde, second and third horde. So there are some monsters here, some here, and some here. So each time we kill one monster, our X increases by 1, right? And we did one operation. So first of all, what we can do to solve this problem is, first of all, sort our monsters, like horde, number of monsters in a horde, in increasing order. Why? Because see, the X operation, the operations that, see how many operations do we actually have to do? Let's suppose we have sorted our hordes in increasing order. So first we'll try to accumulate, like we'll try to increase, like let's suppose we'll try to bring X to a value. And then what we can do for all, like the remaining, once we have that much X, like we have killed, the number of monsters that we have killed is equals to the number of monsters that are remaining. We can simply use these, that is counter, that is combo attack, to kill the remaining monsters. Why? Now you might think like it is not possible because X might be larger than this or X might be larger than this. See, first of all, forget about that condition that you can only kill using combo attack when you have like when you have this X, and if you do a combo attack you will kill X monsters and this will become 0. This is what is combo attack, right? You should have at least X monsters in the horde if you're killing using combo attack. But let's say I'm saying that instead of doing like this, let's convert this problem to each time when you a kill a monster, your X increases by 1. And finally what you can do, you can choose any like y less than equals to X, and you can choose a horde and kill monsters in one operation. You can kill y monsters, so X will decrease by y and y monsters here will die. Did you get the problem? Like instead of killing all the monsters equal, like the number of monsters that are being killed is X in the combo attack that is given the problem, right? I'm saying you can choose any y less than equals to X. It doesn't have to be exactly X. Is it clear? Only this thing, like instead of taking, like if you're doing a combo attack you have to choose a herd which is having exactly like at least X monsters, right? I'm saying this condition doesn't exist. You can take any horde which is having any number of monsters and you can kill those monsters. Let's say you suppose you killed Y monsters, so your X will decrease by Y. Is it clear? This is the problem. Only that condition doesn't exist, that there should be at least X monsters in a horde to perform a combo attack. Now, if you have to solve this problem, how would you have you solved this problem? First, you would have tried, like you would have killed exactly how many monsters? You would have killed, like let's say there are total number of monsters, like total number of monsters means all the monsters in all the hordes. So you will kill exactly total by 2 monsters, seal of this. And now you have X exactly, like it is enough to kill the remaining monsters, right? Yes, no, right? You would kill exactly total by 2 monsters, and then you have exactly like those are the remaining monsters, right? Total by 2. So you have X this much, so you would kill one by one there. But the thing is, each time you change a horde, like here you performed one operation, here you performed one operation. So each time you choose a horde, it takes one operation, right? For this. So we'll try to minimize the number of hordes. So basically these hordes should have maximum number of monsters and these hordes should have minimum number of monsters. So now if we perform the same, like the problem is same that we can choose any y less than equals to X, what we will do, we'll first go in increasing order of these like horde sizes. We'll try to kill monsters until we reach this number that we have killed exactly those many monsters which are now left. After that, we just need to count how many hordes are left, and that is our answer, right? Like number of monsters that we have killed in this plot plus number of hordes left, right? Now the thing is how to connect this problem with our initial problem. So both are same only. Why? Because you don't have to keep increasing your X. Your X is increasing one by one. It is going 1, 2, 3, 4 all the way up till X, right? So if at a moment you are saying that, okay, finally my X, if I do follow this approach, my X will become larger than the size of these hordes and I cannot perform any operation. You went through this path, right? So if the size of this horde was 4, you could have chosen 4 here, right? Your X would become 0 and this horde will get, like all the monsters in this horde will get killed. So the problems are same only. So what is the solution? Just sort your horde sizes in increasing order. Try to kill monsters in such a way that the number of monsters killed are equal to the number of monsters left. Now your answer is nothing but the number of monsters that you have killed plus the number of hordes left. Is it clear? There is only one thing now, that is, let's suppose you have killed, like first horde was having 5, 5, and the next is having 6. So if you kill these 10, it is more than or it is more than or equals to 6. That is the number of monsters left. But we can have a better thing here. Like the answer right now is 10 plus 1. 10 is the number of monsters that you have killed. 1 is the horde left. So instead of doing it like this, what we can do, we can increase our horde by 1. Like we won't kill every monster in this. We'll kill only 2 monsters. How many monsters should we kill? We should kill 3 monsters here. If we kill 3 monsters here, we will have 8 monsters that we have killed, and we will have 2 hordes left. One is this horde, and 2 monsters are left in this horde, right? So 8 plus 2, this gives us better answer. 8 plus 2 is 10. So this is the check that we have to do. So let me show you the implementation. I think it will be clearer after that. So first take n as input, then take array a as input. After sorting it, these are the total number of monsters. Now, like you can initialize your answer to anything. Sum is the number of monsters that we have killed, and count as the number of hordes left. So for each horde sorted in increasing order of the number of monsters, we have killed these many monsters now. Total number of monsters left is this much, and number of hordes left is this much. If I find at any instance that my total number of monsters left is less than or equals to number of monsters that I've entered loop, if condition, I'll check if total is less than sum. This means that I have killed more than I require. So I'll find divided by 2. Not kill half of them. Like I'm killing, let's say I'm killing here. I was killing how many extra? The difference 4. So I was killing 4. So I'll try to not kill 2, and basically my 10 and 2, which is 8. The remaining will be 6 plus 2, which is also 8. This is what I'm doing here. So basically undo this much, and was nothing but the number of hordes left, right? So finally, this is like just an assertion. On the monsters that you have killed, the number of hordes left. Finally, we can do this once the condition gets true and when enter answer. Hello, I'm audible, right?
Yes.
Okay, I got disconnected somehow. Is my voice breaking? Hello?
No.
Okay. Like if in case it starts to break, let me know. So basically we like this, I was able to explain this much, right? You got this part. So I'll explain this from here again. So if total is less than equals to sum, we'll enter this part. If total is less than sum, then this simply means that we have killed more than we require. So we have killed these many. This is the value effect, and now these are the only left. So what I have done, I have taken the difference between these two and I'm dividing it by 2. Why? I'll not kill these many. So basically doing the same thing here. So let's suppose in this we had killed 10, right? And the remaining were 6. So the difference was 10 minus 6, that was 4. So we'll not kill 2. Why? Out of these 4, so the number of monsters that are killed are 8, and this is number of monsters that are left is also 8. So basically making these equal. So decrease this x from sum, that is the monsters that you have killed, and increase your total by x. Finally, your count will also increase by 1 now because the number of hordes that you have to choose is increased by 1 because the current horde doesn't have 0 monsters in it. You're not killing every monster. So finally, your answer is nothing but the number of monsters that you have killed plus the number of hordes that have monsters left in them. So then we can print our answer. Is it clear? Yes, no. Is it clear to everyone? What about others? Okay, it's clear. So let's go to the problem F. So in this problem, we are given that we have a rooted tree with vertex 1, and initially it consists of a single vertex. Now, there are two types of queries that we have to do. We either have to add a node to some node, like some node given in the input, or we have to add x to the numerical values of all the vertices in the subtree of V. Finally, we have to print the numerical value of each vertex. So the types of operations that we have to do is either we need to add a node or add some value to this. Add a node or add some value. Add a node or let's say add some value. So what we can do in the beginning only, we can create this full tree. Like we do all these types of operations earlier. So let's say this final tree. We will note down the time at which these vertices were connected. So we'll add the time at which these vertices were connected. So time for each vertex is noted down. Then let's suppose if we have to add something like this, something was added to this vertex and it was added to time 3, 5, and 7. So what we can check, we can simply do like these are the query times when something was added to this vertex. So we will add everything to each and every of these nodes. Like we'll try to add everything to nodes. What we have to, let's suppose if this node was added at time 6. So the values that added to this node at time 3 and 5 shouldn't be added to this node, right? Only the value which was added at time 7 when actually exists, that should be only added. Are you getting my point? Can someone confirm that I'm audible first of all? Okay. Is this making sense now? If it is not, like ask me, I'll explain it further. Otherwise, we can move ahead. Like basically, this is make it completely considering only second type of query. And then once you have this, note the time for each node. Like this node was connected at this time, this node was connected this time, this node was connected this time. So let's suppose for this node, you added some values at 3, 5, and 7 time. At 3, you added 100. At 5, you added 50. And 7, you added maybe 10. So add 160 to each and every node here. But the thing is, you shouldn't add the values which were added at time 3 and 5 to this node because it was added at time 6. So we have to remove all the values that we have added so far that were added before the time when this node was attached. So how to do that? Basically, this is a segment tree problem or Fenwick tree. Like you just have to remove the sum of the values that were added in this time range from 1 receive this 5. All the values that are added in have to remove those. And you have to print the value of each node, numeric value of each node. Is it making sense? Yes, no? There, this is okay to maintain a Fenwick tree or a segment tree. And for each node, let's suppose we know that at time 3, each node at will at time we will add, let's say at time 5 we will add 50, and at time 7 we will add 10. Now we go to the children nodes, we'll take some value with us, like that value. You can do it using maybe using another tree or inventory, or can do that simply using maintaining a val, which is nothing but the value which we get in the nodes from the nodes ancestor nodes. So we'll add val to this while performing DFS. Now, once we add val, we have added everything that was added to these nodes during the complete timeline. But we have to remove those values before this in the tree. So how to do that? This node some of these here these values were added, right? So you add values from this node. Variable here, have used another theory. The door, I have the Euler instead, like not Euler door, like just, and then we can add like what is to a sub this tree. If we have to add, so what we can do, we can the start node, like first node which is related in the subtree of this. So for all in this, like in the range, we can add some x. But not to complicate like this much, the problem is simpler. We can just have a val variable maintained. So is my voice breaking right now? Yes, no. Okay, and you're writing in the chat, like just unmute yourself and let me know at that very instance, because possible I look your like comments in the chat at a later moment. So what we have done, like I have complicated it unnecessarily, but if you got the idea from here, the implementation will be a little tedious, but it won't be that much complex. Like it won't be that much hard to implement. It will be a little long and it will be a little tedious. So I have taken n as input. Then this is my tree that has going to be finally built. So these are the number of nodes, like for the size of my current tree used for like adding nodes. This is the time at which the ith node will be added. This is the value, like the ith node, what all values are getting added and what is the time at which they are added. So first I'm taking the complete input. For query of type 1, I'll include like add this. I think I was earlier saying query of type 2, but it is query of type 1. We'll add the vertex to our tree, and then we will have its time as q plus 1. Like simply q, like q is the index query number, right? If it was query of type 2, then in val added, I'll include that value added at vertex v is nothing but at this time x was added. Then finally, I'll have this DFS. You don't have to do this DFS. I'm just ordering like having this DFS done so that I can add those values. But instead of doing this, you can have a value variable. So like this will be later used to add values. But instead of doing that, we can simply do it using one variable only. I'll explain that thing. So this is the second DFS. In this, see, first of all, when we come to a vertex, here you have to add everything to a val variable. Here I'm adding everything to the subtree right directly. But instead of doing this, what we can do, we can maintain a val variable, and to that we will just add the value. Something like, let me write it. So take a long int variable called val, which is initially 0. And then for what we can do, instead of doing this, we can have something like value plus equals to simply t, right? And we'll have to do this. Like what we can do, we'll do value plus equals to x, not time, but its value. And then we can completely omit this. Second will be like this segment tree will be used for time. Like at this time, this much value is also added to a node. Then what we can do, answer of u is nothing but the value which is at this node. So instead of doing this, the answer for this will be val only because of everything. And here I'll decrease. After this, the solution is quite straightforward. If the node is more than one, we'll have to subtract everything that was added. What is vertex added? It is nothing but the time at which this vertex was added, right? So for that, we have already added at what time, what value is being added. So you can decrease from your from segment tree, you can get the value of all the things that were added before this node. So after that, just perform DFS, and this value was like this is for removing that. This is for removing the contribution at x, like at time t, because of node v, node u, and then we also have to do like we'll have to decrement our val, right? If you're not using two segment trees. So val minus equals to, so this should also work fine. So finally, we can print answer for each and every vertex. Is it making sense? Like the logic is straightforward, but you'll have to implement this segment tree, or you can just like take it from GFG or at the websites. So, but the idea is simple. The implementation will be a little tedious, but the idea is simple. So hopefully this is clear. Like anyway, like if you have any doubt, once you like actually solve this problem, like just let any of the mentors know. They will be there to help you. So thanks for joining, and bye-bye.